This video is about D6, the photoelectric effect. The photoelectric effect is where electrons can be emitted from the surface of a metal when it is illuminated with electromagnetic radiation of a high enough frequency. Electromagnetic radiation is transmitted in packets of energy that we call photons. The energy of each photon is directly proportional to the frequency of the electromagnetic radiation, and the constant of proportionality is Planck's constant, h. This photon is absorbed by the surface. So what happens to that energy? Well, there's an amount of energy that must be given to an electron within a metal for it to leave the surface of the metal. It's called the work function. And please do not get this confused with ionization energy or removing electrons from atoms. This is a different phenomenon, although related. It's a different phenomenon where the electrons that are being emitted from the metal surface are delocalized electrons already. What I mean by this is that the electrons that are emitted were from the sea of electrons and were not bound to single atoms. The work function is the amount of energy that must be given to an electron for it to leave the surface of the metal. If the energy of a photon is less than the work function, then a photoelectron cannot be emitted. When the energy of the photon is equal to the work function, then the frequency of the electromagnetic radiation is called the threshold frequency. And we can indicate that with a subscript 0. It is the minimum frequency that will cause the emission of photoelectrons. Any frequency higher than this threshold frequency will still emit photoelectrons, but there'll be some energy left over, and that is the kinetic energy of the photoelectron. Any current has a heating effect, transferring energy into the thermal energy store. The electron moving through the metal, well, it is a current, and therefore work is done as the electron moves through the metal. That's before it reaches the surface. Now, whilst you have to know that for your A-level, for any questions that deal with the mathematics of the photoelectric effect, you don't have to worry about that. And so we will be looking at the maximum kinetic energy that an electron can have, assuming that the electron is liberated from the very surface of the metal, and so no work has been done bringing that electron to the surface. So our equation for the photoelectric effect is essentially energy in equals energy out. The energy in is the energy of the photon, and the energy out is the work that has to be done against the work function, and plus whatever is left, the spare change of the transaction, which is the kinetic energy of the photoelectron after it has been emitted. But what if we have a second metal surface and there is a potential difference between them? If the lower metal surface is set at a positive potential and the upper surface is pinned at 0 volts, for example, then there will be an electric field travelling on this page upwards, and therefore the electrons would feel a uniform force downwards. Alternatively, we could have a negative potential at the top and 0 potential at the bottom, or a negative at the top and a positive at the bottom. Either way, between these two metal plates there will be a uniform electric field, and the electron would feel a force in the opposite direction to that electric field. In this situation, the photon is absorbed, so HF energy is absorbed, and phi, the work function, has been spent getting the electron out of the surface. It leaves with an amount of energy, EK max, but then as it ascends, it's doing work against this electric field, and so it loses kinetic energy. It slows down. This shape here should be familiar to you from mechanics. It's a parabola. And because in a uniform field the electron feels a uniform force, that means that the electron is following the usual two-dimensional parabolic motion associated with projectiles. In fact, A-level questions could ask you about projectile motion in this context. Now, if we assume the electron is emitted directly upwards, and therefore its velocity component is upwards, it's going as fast as it possibly could in the vertical direction, then it has got the best chance of reaching the second metal surface. Once the electrons reach the other metal surface, it can be conducted away, and we'll have a current between the lower surface and the upper surface. But if the electron is not able, it's impossible for it to reach the top metal surface, then there can be no current flowing from the bottom surface to the top surface. Or indeed from the top surface to the bottom surface, because electrons are negatively charged. The work done moving an electron across a potential difference V is equal to the charge on the electron multiplied by that potential difference. If the maximum kinetic energy that the electron has is less than the energy that would be required to move the electron across that potential difference, then the electron never reaches the second metal surface and falls back, and no current will be flowing. The electrons will still be leaving the surface, but they will be returning to the same surface. There is a threshold condition where the kinetic energy, the maximum kinetic energy that the photoelectron has when it leaves the surface, is equal to the charge on the electron multiplied by that potential difference across those surfaces. In that case, we call that potential difference the stopping potential. Any potential greater than that stopping potential will stop the current. But any potential lower than that stopping potential would mean that EK max is larger than EV, and so there would be a current detected because the electrons would be leaving the lower surface and reaching the upper surface. Now this is all very complicated, but it basically means there are three equations that you need to concern yourself with. The first is the equation for the photoelectric effect. This is where you calculate the maximum kinetic energy if you've got any frequency, and of course if that's negative it means that there is no photoelectric emission. There's the equation for stopping potential, which we've just gone through, which is this threshold condition where the potential is exactly right to just stop the electrons reaching the other surface. Any higher potential, no electrons reach the second surface. Any lower potential, and they do. And the final equation is the threshold frequency, which is where the kinetic energy of the photoelectrons that are emitted from the surface is zero. That threshold condition that allows photoelectric emission, but nothing else. Now, a tricky part of questions to do with the photoelectric effect is that often energy will be given to you in units of electron volt, and you'll need to convert. So 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. What this means practically is that if you're converting from electron volts to joules, you multiply by 1.6 times 10 to the negative 19. And if you're converting from joules to electron volts, you divide by 1.6 times 10 to the negative 19. And if the units are given as mega electron volts or kilo electron volts, you have to include the multiplier, the prefix as well. There's one question on D6 called D6.5 that uses this equation here, and is going to ask you to rearrange that equation in the form y equals mx plus c, so you can examine what the different features of the graph will look like. Well, I'll tell you this is the equation you want, but I'm not going to go through the answer to that now.